Okay, sounds good. Welcome back, and we are going to now take a relatively long ride. So it's going to take a little bit of time to rederive the Bellman's equation for the discounted task in a different way, which from the beginning takes a completely different path. And as I anticipated, has several advantages in the sense that it allows us to introduce many concepts that we will be working on in the following lectures as well. So since there will be many things coming in, many interesting ideas and techniques and approaches that also have an interest outside of the specific problem at hand, I urge you to stop me at any given time if you can't follow, okay? And I can then sort of take a short break in the narration to explain some similar aspects, or refer you to the relevant material. It doesn't matter if we can't close it until the end of today. If needed, we can overflow on that next lecture, even though I think we can make it, but we'll see. Okay, so let's start all over again from the beginning. The goal is to find the best policy, which is a collection of probability distributions over actions given states. So the best policy in order to maximize the discounted, maximize discounted cumulative reward, also said the return. All right. So the idea here is that we don't start from introducing the value function and taking the optimization over the value function and deriving the Bellman equation that way. We look at this problem from an entirely different angle. What's the angle? Well, this objective here, our G function, depends on the policy, of course, because that's what we want to optimize over. So why don't we just focus directly on the policy? Okay, so let me elaborate on this. So our G function is something which maps policies into real values. So what is this? This is not a proper notation for a function. I should put the domain here. So what is the domain of this function? Well, it acts on the following space. So what are policies? Well, policies are probability distributions. Okay, there's one probability distribution over actions for each state. So what this object here is, in fact, is the simplex, okay, delta. I will explain what it is in a second, over actions, and there are capital S copies of it. Okay, so this is the space where policies live. Policies belong to this set. Let's get more clear. What is delta K? So delta K for any integer K is called the simplex. Is a set of real vectors x which belong to Rk such that they are all non-negative. Okay, so they live in the orthant, as it's called, and they sum up to 1. Okay, so these are legitimate probability distributions over a set of k possible values, say k possible events. Okay, so delta sub A means that this, I'm caring here about probability distributions over actions, and there are number A of them. This is the cardinality of the set of actions. And then I have one of this probability for each state. So there is the product of all these simplexes. So how does a simplex look like? Well, for instance, take k equals 3. Okay, so this would be x1, x2, x3. I'm carrying only positive values, so it lives just in this orthant. And then I have to impose that the sum of those is 1, which defines a plane. Okay. So this object here, this triangle here is sigma 3. Every probability distribution over 3 values, over 3 possible outcomes, sits on a triangle. And this triangle is a simplex. Okay. And then I have as many of those as states I have. So in our case, we have, for state 1, we have one simplex. For state 2, we have another simplex. Okay. And then we have the simplex for state capital for the number, the largest item in the list. Okay, all of these are triangles or tetrahedra or hypertetrahedra or whatever. Okay, and so a point on this triangle is a policy for state 1. This is a policy for state 2, including possibly points that are on the vertices of this set. Okay, on the boundaries. This is possible. For instance, sitting here on this, on the tip of this, what does it mean? Well, it means that x1 and x2 are 0 and x3 equals 1, which means taking a policy which always chooses action 3. And if I sit here, I always choose action 1, and if I sit here, I always choose action 2. Anything which is in the middle is a random policy which chooses some fraction of probabilities. Okay, so far so good. So our domain for the policy is just this set here, which is the product of all these triangles. The first interesting remark to make is that this is a convex set. Okay, remember, the intuitive idea of a convex set is a set which is like a ball, okay, so to speak, in the sense that if you take any 2 points inside this set and you join them by a line, every point in the middle is within the set. Okay, so let me draw this. So this is a convex set because every couple of points I take, and if I draw a line between them, this is still, any point on the line is inside the domain. This is the definition of a convex set for any pair. This is a convex set. Well, clearly, a banana-shaped set is not convex because if you take points on the 2 tips, they go outside the domain. Why this is a convex set? Well, this is very simple because if I have 2 sets of policies, pi 1 and pi 2, and then I make a linear combination, lambda pi 1 plus 1 minus lambda pi 2, okay, which means drawing this line, basically, because for any value of lambda comprised between 0 and 1, I move on a line between this pi 1 and pi 2. Okay, so lambda 1/2 would be sitting here. Here I am when lambda is 1, and here I am when lambda is 0. Okay, then you can clearly see that if I make this linear combination of 2 probability distributions, this still is a probability distribution, okay, because it's positive and it sums to 1. It's straightforward. So this is a convex set, which is good. Okay, it's a nice property. We will use that in a second. What we want to do now is basically we want to find the maximum of this G function over this space. Okay, So again, at a very abstract level, so this is my state space and everything is mapped onto the real axis, okay? This is where the G function lives. It's a real valued object. It's a number, okay? A real number. So again, abstracting away. So if this plane now here is my space of simplexes, okay? So this is the convex set. This is delta S, sorry, delta A to power S. Then my function G is some object like this. Okay, I'm trying to draw a surface here. So from every policy here, this is a policy. From every policy, I get a G value. This is G of Y. And if I move around in this convex space of all policies, I get different values. Okay, so you can think this as a sheet which is lying over the domain. Are we all on the same page so far? Just to visualize what the thing is. Everything is taking place in very high-dimensional abstract spaces, but this is the intuition. So the optimization problem, what is it? Well, we have to find where this sheet of values, which is above, reaches its maximum. So there is a point here where I have my G star, my maximum, which corresponds in this horribly drawn graph to some point inside this domain where I have my optimal policy. Okay, so in very abstract terms, this is a problem of optimization over a convex set of a relatively complicated function. So we want to tackle now this problem right directly, okay? So the first thing that we need is that we need to express what is the condition for a function to be at its optimum in a convex set. And this is given by the so-called first order optimality conditions. Okay, so what do these conditions say? Well, again, let's consider that you have again this convex, not so convex set, okay, which we call D. This is a convex set, and there is a function from X here to some f of X on the real axis. Okay, so there's a function on the ball. Think about a function on the ball. So we have that if X star belongs to the set of maxima of X, okay? So if it is a maximum, X star is a point where this is maximum. It could be either inside or on the boundary, doesn't matter. Okay. Then this is equivalent to asking that the gradient of f in X star times X star minus X must be non-negative. So where does this condition come from? Let's split it in the two cases. So f is also a convex function. Okay. So if X star belongs to the interior of D, okay, so it's not on the boundaries, then as usual, you know that the maximum is a stationary point. So in this case, we have the gradient must be 0 if it's inside. Well, but this inequality, I have also a larger equal than 0. It comes from the fact that sometimes you may have a maximum on the boundary, and you want to account for that as well. So in that case, what is geometric intuition? Oh, well, let's have a look at what happens here. So suppose that your x star is on the boundary. So here is where your function f is the largest. So if you look close to this boundary, then you will see that these are the level lines. So the level lines for f must be like this. Okay, so f must be increasing in this direction, which means that the gradient must be pointing somewhere outside of the domain. Which means again that if I take any point x here and I take the vector which connects x and x star, which is this one, it must also point outside. The fact that the domain is convex makes the fact that this condition is equivalent to saying if x star is on the boundary, then this object must be strictly positive. Or 0 if it's degenerate, but cannot be negative. You can prove by contradiction that if you assume that this thing is negative, then x star cannot be a point, maximum point. Okay. So this is basically a little extension on the notion, usual notion of stationary point. So if x star is on the boundary of D, this works as well. Fine, we will use that at the very end. Okay, so just keep it in store. The basic idea here is that this motivates us to try to compute the gradient. So what we're going to now do is find a way to calculate the gradient of G. If we are able to compute the gradient of G, that is the derivative of G, so how G varies depending on how we move in this policy space, okay? So pictorially, the gradient of G is a vector which points like this. Can you see? It's sorry, it's a bit blurred. Let me draw that again. This one's sharper. So there is, at any point where there is a policy pi, there is a G value and there is a gradient in this space. And if we can compute the gradient of G, we can see where this optimality condition, this first order optimality condition is met. But we have to compute this gradient first. And that's what we're going to do now. Again, gradient with respect to what? With respect to all possible components of the policies, okay? So it's a relatively complex object, but let's go one step at a time. And the first step in this is, we want to rewrite G in a simpler way, okay? So we have to manipulate a little bit our G, which, remember, is this expectation value. We want to rewrite it a little bit in order to make our goal of taking derivatives of G easier. How does that work? Okay, so G is, once again, this object here. And then, of course, this expectation value, we have to make it explicit in terms of probabilities in order to make any analytical operation on it, any derivation. So what is it? Well, we can rewrite this as the sum t going from 0 to infinity, and then we have to take the expectation value of this object, okay? So we're going to sum over all possible values that are taken by these variables, S, A, S prime, with their own probability, okay? So it's going to be If I'm in state S, I am picking action with the probability pi, and I will end up in a new state S prime with probability P. Then there will be RSAS prime. But what is left? I have to specify what is my probability of being in state S at time t, okay? So what is this probability of being in state S at time t? Let me write it explicitly. It's just the probability of being, of that ST is equal to S, given that at the initial time, my S naught is something like another S bar. And then I have to consider the probability of the point where I started from, and I have to sum over that. Okay, so recap, short recap about this single step. This average here is the sum of many terms over time. First sum here. Of what? Well, my process starts from an initial state S bar with a probability rho naught. Then in T steps goes to a state S with a probability, this one, which I'm not writing yet. We will sort of unroll it in a second. And then once I am in state S, I pick an action A with probability pi. I end up in a state S prime with this probability, and I receive an average reward, this. Okay, so this is just the explicit way of writing this object. Good. So next step, what is this? Okay, now here is where the Markovian property of the system comes into play, because the probability of being in some position, in some state after T steps is the product of probabilities of making single steps. Okay, this is the Markov property. If you go there in T steps, you have to make T small steps to go there explicitly. So the probability that ST is S and S0 is S bar is what? Well, let's go back one step at a time. This is equal to the probability being S, given that at previous time I was in another point, say S tilde, times the probability that at time t minus 1 I'm in S tilde, and the initial time I'm in S. And this is summed over all possible intermediate states S tilde. Okay, so this is the Markov property. I go to S through an intermediate step S tilde at the previous time. And then there is the probability of everything that was happening before that. And I can go on with this, right? So I could unroll at the next step, so on and so on and so forth. But what I want to do here is simpler at this step, in the sense that it's useful to move to a description in terms of matrices. Okay, so let me define a matrix PT with indices S and S bar. Okay, so these are the rows and these are the columns. And this is a matrix, a square matrix. So this object here is exactly this thing, by definition. So what is this equation on above here telling me? Well, this is again a matrix, and this is the same matrix, but for t minus 1. So this is, in fact, a matrix capital P S tilde times P with index t minus 1 S tilde S bar, sum over as tilde. But then you realize here that, well, this thing is defined by this, okay? So this object here is what I'm redefining here, like this. But you realize that this is a product of matrices. I'm just taking columns times rows of the new matrix. So in short, this tells me that the T matrix is just this P matrix to the power T. So this is P times P times P, T times. What I'm doing here is I'm just refreshing you about how to describe Markov chains with matrices. Okay, I'm just doing it for our specific purpose. So what is explicitly this P S prime S matrix, for instance? Well, this is the one-step probability, okay? The probability of going from state S to state S prime. So this is, in our case, sum over all the policies, S prime, that's A. So you must remember that all the times that this capital P matrix that we are dealing with, this green one, it's always the same object, depends on pi implicitly, okay? Because when we have to take derivatives, we have to remember which things depend on pi and which don't. For instance, here in this sum, row node does not depend on pi because it's the initial condition that we choose. It doesn't depend on the decisions that we'll make in the beginning. But this object depends, and of course, pi is there. So when we have to take the derivative, we have to take the derivatives with respect to this dependence and this dependence, but not this, not this, not this. Okay, so now another little step in definitions. It's useful to consider here these following terms. So when we take the sum over here, the sum over S and A prime only affects these terms here. The yellow is one here. So it's useful to define another object, which I call capital R of S, which is defined as the sum over S prime and A of pi AS, P of S prime SA. So what is it? This is the expected reward from a state S. If I'm in state S and I use policy pi, this is what I'm going to expect for the next step. Because I'm in S, I take action A according to pi, I end up in state S prime according to P, and I collect my average reward at RSA S prime. Remember, this object here, which is the one that is appearing here in yellow, orange, whatever, also depends on pi. We got to remember this when we take derivatives. Okay, then we can collect all this information here from this formula, and we can rewrite G in a different way. So after this introduction of notation, I am allowed to rewrite G in the following way. Sum over S of what? Well, the sum of, in yellow, I can make it. I define this as capital R of S. Okay, so there was a sum over time before everything. Sum over time going from 0 to infinity. There is a sum over S of R of S. Then there is a gamma to the T, which I sort of forgot here, sorry. And I should better put here as well. Okay, so this is my reward, and then I have what? This transition probability that I'm gonna put in blue, okay, which is the same that is here, and the same that is here. Therefore, it's this one, it's the product of these p's. So what I have here is, let me write this as this p to the power t components s bar times rho 0 of s bar. Okay. I'm just for now fumbling with the definitions in order to rearrange this object. But now things become even, sorry, there is also a sum over s bar here. But things here become even more friendly from the viewpoint of calculation, because again, this is a matrix. This can be seen as a vector, a row vector. So we can introduce R as a row vector. And we can make a row node a column vector. Sorry, I take this back. Let's make them both column vector. And then this means that I can write G as a sum from t going to 0 to infinity of gamma t. And then I have R transpose p to the power t rho 0. Okay, so this is already very compact. It's the transpose of a column vector is a row vector. This is a square matrix. P to the power t is a square matrix. And row node is a column vector. All these live over the space of states in R real to the power number of states. I mean, you don't need to follow step by step everything I say. Just acknowledge at this stage that if you sit down, you can try work all the steps back. There's nothing which seems obscure or totally absurd to you. Okay. If, on the other hand, if this is the case, you must absolutely stop me. Very good. We are almost done here. We can even go a little step further, because here there is an interesting object. So let me do a further trivial manipulation. But now you see that this object in brackets, this looks like something familiar. This is a geometric sum. So I can sum formally this thing and write it as 1 minus gamma p. So this is the identity matrix. This one here is the identity. And this is the inverse of this matrix times rho 0. Let me open a parenthesis here. We're going to take a quick detour to prove this, because it's very simple, but let's prove it. I'm a little bit embarrassed at writing proof for such a simple thing, so I will not do that. I will just write it. That's it. So 1 minus gamma p times this sum So let's write it. What it is 1 minus gamma p times 1 plus gamma p plus gamma squared p squared plus etc. And when we just distribute the product, we get 1 minus gamma p, then this times this plus gamma p, this times this minus gamma squared t squared, this times 1 plus gamma squared t squared. And so you see that this cancels out, etc. So this gives 1, where 1 is, again, the identity matrix. And this is the usual trick you do for geometric sums of real numbers, but you can do that for matrices as well. What is the important point? The important point is that this series here, must converge. If it converges, then you can write it like this. Or in other way, that's the same statement. This matrix here must be invertible. Okay. And then I just quote here a result from the linear algebra that says that P is stochastic. Okay. What does it mean that P is stochastic? Well, it's a matrix which describes probability transitions. We constructed like it. Okay. So it's positive, and the sum of the elements of each column must sum up to 1, which is probability conservation. Okay. So this is what I say when I say it's stochastic. It's the definition of what a stochastic matrix is. So is a stochastic matrix. This means that the spectral radius, which is a fancy name for the modulus of the largest eigenvalue of P, is smaller or equal to 1. This is a small part of a bigger theorem, which is called the Perron-Frobenius. Here. Okay, it's linear algebra. But this is enough for us, because if this is true, then this means that gamma p, the eigenvalues cannot be larger than gamma lambda max modulus, which is in turn smaller than equal than gamma, which is in turn smaller than 1. Okay, so therefore, if this guarantees that 1 minus gamma p is invertible. Okay, so again, many details. The basic idea is that if you use custom tools from linear algebra, you can prove that you can invert your matrix here. So this expression finally makes perfect sense, which I summarize here. Recap, sorry, there's no gradient yet. I'm running ahead of time. Recap, we can write G as a simple object, which is just R transpose 1 minus gamma p to the minus 1 rho 0. Where remember that we have these definitions in yellow here and in green here. This was defined here, and this was defined above here. Okay, now this puts us in condition of taking gradients. Now we're going to take gradients. For the moment, for the sake of simplicity, I'm just going to take, I'm going to write this, grad G. So taking gradients means that you have to take derivatives in all possible directions of space. Okay, so this my grad C means that I'm choosing one particular direction. Okay, so it's a formal. I don't want to overload the notation here to put gradient with respect to the coordinate I, J, whatever. Okay, for the moment it's just a gradient along some direction in space. Okay, which means that if we go back to our graphical description, we are taking two neighboring points, say pi and pi plus d pi, okay, a small increment in policy, and then we're looking at the gradient along that direction. And we're going to specify the actual direction of it, okay? Are you okay with this notation? Fine. So, well, we have to take derivatives of the right-hand side with respect to the policy, but these things that I highlighted in orange and in green depend on pi, okay? So let's take the derivative and treat these matrices as they should be treated, just like functions of real numbers. So first, I take the derivative with respect to this. I use the chain rule. So this is gradient of RT. This is the transpose, okay? I didn't write it explicitly, but it's better to mark it down. This means transpose, because there are T's all over the place. Nothing to do with horizon, eh? Let's be super clear with that. Okay, so this is the first part of the derivative. Then there is the second part. Again, I'm going very, very slow. And there's no derivative to be taken with respect to rho naught because it doesn't depend on the policy. Okay. Then the first part, we have to live with that for a while. So we leave it as it is. But we can work on the second part. Okay. So what is the gradient of the inverse of a matrix? Here we have to pay attention because we cannot use the usual rules of differentiation because matrices can be non-commutative. So we have to pay a little bit of attention. So you should be familiar with this, but let's refresh this once more. And I'm going to use some pink color for this. So let's consider this thing. So in general, what is the gradient of a matrix -1? So this is the gradient of the inverse of a matrix. Well, there's a very easy way to derive this expression. You just have to realize that m times m-1 is the identity matrix by definition. That's the definition of the inverse. And then we take the gradient of both sides. And this gives grad m times m-1 plus m times grad of m-1 equals 0. This is a matrix of all zeros on the right-hand side. And then what we do is just multiply everything by m-1 on the left. And this becomes m-1 grad m-1 plus grad of m-1 equals 0. And therefore, final step, the gradient of the inverse is minus the inverse, the gradient of the matrix itself times the inverse. Okay, quite straightforward. We can go back to this and say, okay, what happens to this derivative here? So this doesn't look nice, so it's better if I erase this and report this below. Okay, so we know how to do this gradient now. So I'm writing that grad G is going to be our first part. And then I have my second part, which is minus, my matrix M was 1 minus gamma P. So I have RT, which was there, 1 minus gamma P minus 1, the gradient of 1 minus gamma P times 1 minus gamma p minus 1 times no, doesn't want to look like okay. Fine. Now this thing here is simple because this becomes just minus gamma grad p. And therefore I can further simplify and write this thing. Grad RT. Now notice here that we have two parts which are the same on the rightmost part. Okay, these two are the same object. And let me call this thing eta. It's another vector, eta, which I introduce now. And just to write this in more compact form. So this becomes grad RT plus gamma RT 1 minus gamma p minus 1. All of this multiplied by eta. Okay. Again, I'm just at this level. There's grad p here. At this level, I'm just doing some manipulations, rewriting things. Okay. Very good. Now we are closing in on the calculation of this gradient. So let's not hurry now. So two remarks. Remarks number one. This object eta, what is it? Well, eta is defined as the inverse of this matrix times rho naught, which if I unfold again this object using the transition probabilities, it gives me this. But remember that rho naught is the initial distribution and p to the power t is the probability of being in a certain place after a certain number of steps. So this, excuse me, just a second, sorry. Okay. So this leads me to the following expression, that the component S for this is just the sum from t going to 0 to infinity, gamma to the power t times the probability that I am in state S, and this is my matrix P to the power T, and this is rho naught of S bar. Okay, I have to ask you, sorry, apologies, because I have to. Okay. So this means that this quantity here, eta, that we have defined, if you look at this, sorry again. Okay. So this this object here, eta s, in fact, is nothing but the time spent in state S before the process dies. Okay? Because remember, gamma is the survival probability. So gamma to the power t is the probability of having survived after t steps. And after t steps, you will be in state S with this probability. Okay. So this is exactly, so this thing is exactly the probability of being in state T after state S after t steps. Okay, so this is just to give you an interpretation of this abstract quantity that I introduced. It has a meaning, and being the time spent in a given state, it also has a consequence that this eta of S, if the process is nice enough, is something which is strictly positive. Because if it were, it's positive, it's not negative because the probabilities are positives, gamma is positive, everything is positive on the right-hand side. And it's not strictly zero because this would mean that there are some states which are never visited, which is never the case. Okay. Unless you focus, I mean, let's not spend too much time on the details here. Okay. This is the first remark. The second remark, which is very important, is that when we look at this term here in red, let's say we call it capital V. Well, the important thing is that this is the value. This is the same object that we introduced at the beginning of our lectures. This is the value. So the entry S of this vector is the value of state S. Why is that? Well, again, it's pretty simple. You just have to do the same process I did here. Write this explicitly. So V of S here is sum over t going from 0 to infinity of gamma t of what? R transpose, which means I have to sum over sum S prime of capital R S prime. And then I have the probability that ST is equal to S prime, given that S0 is equal to S. But this is exactly the definition of the value function. It's exactly the expectation of what I get if I start from S and I end up here. So this is exactly expectation of sum over t going from 0 to infinity of gamma t of capital R of ST. And you remember that by the definition that capital R of ST is defined somewhere up here, this object here, which is also the expected value of R ST AT ST plus 1 conditioned on ST equals S. So that here below, this is also equal to the expectation value sum to infinity gamma t small r ST AT ST plus 1. All of this is not a chance, I mean, because we are doing essentially getting towards the same final result. So it's not surprising that we see the same objects popping up. So when we recollect all this, our almost final step says that the gradient of G is equal to the gradient of R transpose plus gamma, the value function transpose times graph P times theta. Okay, it's a rather compact description. We're almost done here. We just have to compute these objects, these gradients. Start from this. So what is grad R component S? Well, it's the gradient. I use the definition, which is sum over S prime A of pi A S S prime say S prime. And of course, the only thing I have to act upon is this. So this is just sum over S prime A E of S prime S A S prime grad pi A S. Okay, it's a linear function of the policy, so it's easy to derive. And same here. This is an object which has two indices because it's a matrix. It's the gradient. How was this defined? It was the sum over all actions of all possible transitions. Okay. So when we make these products explicit, we end up with writing the gradient in the following form. Sum over S A S prime E of S prime S A. Then we have R of S A S prime plus gamma S prime times the gradient of pi. So this was a long route for a very neat result, in that we have been able to express the gradient in terms of derivatives with respect to the policy itself. Everything else in the middle is something which depends on pi, so V depends on pi. But it just depends on the gradients in such a way. So we now just have 5 minutes to conclude, and we're going to show that the optimality equation, the optimality conditions, the first order condition, okay, for optimality that I wrote earlier, is satisfied by the choice which is given by the Bellman's equation. So what is the connection with the Bellman equation? Well, the connection is given by this term which appears here. So this object in front of the gradient is the one which appears in the Bellman equation. So that's where the two ends meet. So let's do this final step. And this final step goes as follows. Now it's time to take the derivative with respect to some specific directions. Okay. So now here I specialize and I say that I'm taking this object becomes the partial derivative of G with respect to the policy which has a certain state and a certain action. So let's roll back to our geometric interpretation of the beginning. Here. So this is the space where my independent variables live. So now I'm focusing on one particular state, and I'm focusing on one particular action. So I'm taking the derivative in this direction. More explicitly, if you wish, you have to think that G is a function of what? Of the policy that chooses action 1 in state 1, of pi of 2, 1, of pi of the last available action in state 1. But it depends also on, sorry, 1, 2, 2, 2, and then by 1 for the last state, pi, capital A. So it depends on all these entries. And we're going to take a derivative with respect to one of these entries here in the middle, anyone. And if we do that, well, what we realize is that this derivative, well, this just selects the entries A and S here. So this gives an identity matrix in the space of actions and states. So this becomes sum over S prime of P of S prime SA R of SA S prime plus gamma V S prime. All this is multiplied by eta of S, which is outside because it doesn't depend on S prime. Okay. Then very final step. So it's useful to define this object, give it a name, which is QSI, which is also the state action value function, also called the quality. So this is nothing but this object Q. You can realize by looking at this formula that QSA is just the expected value gamma T RST AT ST plus 1. But now this is conditioned on the fact that S0 is equal to S and A0 is equal to A. Okay. So it's just like the value function, but now you're conditioning also on the choice of A. And it's easy to check that the connection between the value function and the state action value function is that just if you sum over the policy, you recover the usual value function. Okay, this object naturally comes in this gradient taking procedure. So before the last equation, this gradient is just eta of S, which is a positive object, and then QSA. And then, given the very simple expression that we get here, remember that the first order condition for optimality is that the gradient taken as a vector of G, so there's no dot here, times pi star taken at optimality times pi star minus pi must be greater or equal than 0. Then the statement is that if you take pi star to be argmax over A of QSA, Q star SA, So if you pick your policy from Q star, taking the item with the largest value, then this object is satisfied. Why? Because if you plug this in and take the product, what you end up with is sum over SNA of dg d pi as computed at optimality at pi star. So this is the part that I'm writing here, times pi as star minus pi as. Okay, so this object here, this one, I replace for this expression. This becomes sum over s of eta s q as a pi star as pi. And then I use this definition of my optimal policy and take the sum. So since I am selecting the best action here, this becomes sum over s of q of s a star s. This is the best action. For every state, I pick the best action according to the one in this matrix gives me the largest amount. So this is multiplied. This is the first sum here. And then I have minus sum over a by a q star. Okay, this was a q star. And now clearly, since this object was the maximum, there is no possible way. So for every pi, this object cannot be larger than this, because this was the one that maximized the column by column, this matrix. So I conclude that this must be larger than 0. So what does it mean? Well, it means that Q, remember how it's defined? It's defined by this. Okay. So this means that my optimal policy E star of any state S is equal to the argmax over all possible A of Q, but Q is this object by definition, this one. So this is sum over S prime, P of S prime SA, R of SA S prime, plus gamma V star of S prime. And V star is given by its definition, which is this recursion equation here. So if you plug that back in, you obtain that. What's happening? V star of S is equal to the maximum of A sum over S. And this is the Bellman's equation. Okay, sorry, I overflowed with time. So that was a lot of information, of course, here. The bottom line is that if you follow these simple steps from algebra, etc., they are lengthy, but you can get to the Bellman equation through this very different pathway. And we will use this gradient, policy gradient result elsewhere in the following to construct effective algorithm for the model-free case. Okay, with that, I think if you still have some energy and want to ask for questions, I'm available. Yes, please.
Yeah, Yeah, I have.
I'm sorry. It's impossible, I think, to follow. I wasn't able to follow really what you were saying, and I hardly managed to write anything. To be honest, it's very hard to follow like this.
All this will be available to look back again on the videos, and I can make a recap next lecture to highlight the basic steps.
Yeah, maybe if we can, if we have other, let's say, very computational. Well, this is not computational; it's more mathematical demonstration. If we can have maybe the steps before, it would be much easier to follow, because like this, I think at least I wasn't able to really follow, and I think there are lots of errors in the script that I tried to copy. It's very hard to follow this.
No problem. Yes, I know that this was basically the most mathematical dense part of the course, and so I can you can sort of relax for the following. But I understand your concern. There's a lot of things going on here, so I'm happy to get back to this in next lecture and revise all the steps. And meanwhile, you can. As soon as it will be made available on the channel, you can sort of go through the steps itself. And I cannot promise anything, but if I have time, I can write down some notes in LaTeX, which might be more readable.
Or maybe
can I make a question regarding one passage? Why we lost the transpose of the V? Because at a certain point we wrote the gradient of R and the gradient of P, and when we wrote again the gradient of G, we wrote V of S prime, but we lost the transpose.
Well, because that's just the component, okay? So this is just the component of the matrix. It doesn't matter whether it's a row or a vector. It's just the item S in the matrix, in the vector. So I could have written this VTS, but that doesn't matter. It's just a real number.
Mm-hmm.
So whether you write it as a column or as a row, that's pretty much the same.
Okay.
Any other questions, Par?
I just wanted to ask if it's possible for you to put these notes you take during the lectures on Slack, so we can have them. And
sure, I can upload the notes on Slack, so you can have them.
Thank you very much.
Sure, no problem.
Sorry, can I make a question?
Yes, please.
But by using this gradient technique, we possibly can reach just a local optimum, or we always find the global optimum?
Yeah, that's the question is correct. So in general, these techniques technique only allows you to get to a local maximum, but as you know from the previous lecture, since the Bellman operator is contracting, there is a unique optimum. So one could go one step further and compute the Hessian of G to show that it's definitely positive. But I think you're overwhelmed, so we're not going to go through down that road. But yes, in general, you're perfectly right. In this particular case, the problem is convex. So that's what it makes the solution to be unique. Does that answer?
So due to the convex domain, we converge to the we have just one.
There are both things that play together: the convex domain and the convex function. When you have both of them, then the solution is unique. Because if you have a convex function in a non-convex domain, you might have multiple minima or multiple maxima.
Sorry, you said we have a convex function in a
convex domain.
Convex domain.
So I discussed about convexity when I said that all these simplexes you can move around on a line from one point to another. And about the convexity of the G function itself as a function of the policy, well, we didn't prove it here, but it was a consequence, it was implicitly a consequence of the fixed point result that we had yesterday. Any other question?
I have a question.
Yes, please.
If we take the gradient of G, we will do this numerically or analytically?
Well, so when you have this expression here, which is in front of you, you can compute it numerically as follows. So you have a policy, you compute your value function for that policy using the recursion. Okay, so you can compute this object using recursion for a given policy. You can compute this gradient analytically because you know what the policy is, you choose how to express it. Okay, so if you wish, go in a little step below this expression here. Here, you compute the value function, and then you combine linearly these objects. You can compute these things also obeys a linear equation, and then therefore you can derive the gradient from these two steps. So it's just a linear operation to compute the gradient. So this also points to the fact that these results produces some algorithms for solving numerically the Bellman equation, and I will tell you about this next lecture. All right. So if you're done,
sorry, I know that it's late. I don't know if the other guys
no problem.
are interested. Another math doubt that I have is when we are writing the gradient of G up, if you can go a little up, I have from gradient of R a sum over S prime and A, and the gradient of P, which is a sum over A. But then in the gradient of G, I have a sum over S, A, and S prime. I don't know why we added that S.
We added this because here I'm missing a piece, which is eta of S, which was always around since the beginning. This product here, that is the index of eta, which is missing here. So you're right, that was something missing here.
Ah, okay.
Over S.
Thank you.
Sure.
Thank you.
Okay, then goodbye, everybody. Have a relaxing weekend and see you next Wednesday.
Bye. Thank you.
Thank you.
Bye.
Goodbye.
Thank you.
See you.
Thank you. Happy holidays.
Good.